So far, we have discussed material concerning mathematical models for the theoretical games that involve strategies that are, in general terms, known as pure strategies. There is another family of games that involves uncertainty and randomness, and in these more general terms, we will classify between pure strategies or mixed strategies, and that's what we will discuss today. And to use reference case study, we're going to review briefly another well-known game known as Hawk-Dove game. Okay, and we're going to use this game as a case study so that we can also introduce some new concepts, introduce some notation, and have a little conversation about what we called evolutionary stability. Okay, so we will extend the definition of Nash equilibrium, and then we have to say something about evolutionary stability. Now, this particular game is going to assume that we have two animals that are competing with each other, and they have to decide how to divide common resources. In particular, they have to decide how to divide some food supply. Okay, so we assume we have an animal species called hawk. We're gonna use the notation H to denote this species, and we're gonna assume this species is very aggressive in terms of this food sharing scenario. And then we have another species called dove, denoted here by the letter D, which is known to be very passive, right? So you have basically a contest between two types of behavior: aggressive behavior characteristic of hawks, passive behavior characteristic of doves. So if the two animals behave passively, then here's where we're going to start using some specific values. This is for terms of making our illustration more concrete. You could denote this as parameter values, constant values, but to be more concrete, let's assume that we have some measure of the gain out of this share of food. So we're going to assume that if we have the encounter of two passive animals, they divide the food in equal shares, and each of these passive animals obtains a payoff of, here denoted with the quantity 3. Furthermore, we assume that when one behaves aggressively while the other one behaves passively, the aggressor is the animal that has the advantage here. This is the animal that gets most of the food. So just for the sake of this conversation, we use the specific values. We're going to say that the aggressor gets a payoff of 5, and the passive one gets a payoff of 1. Okay. I'm not giving you concrete details about what are the units of this. Let's just assume there is a way of quantifying and measuring the gain in energy or other nutrients out of this food supply. So if both animals behave aggressively, then they destroy the food, and each of them gets nothing. So each of them gets a payoff of 0. So with these values of payoffs, we can summarize this information in a payoff matrix that looks like this, right? This is nothing new. So in this game, we would say that the strategy dove-hawk is a Nash equilibrium, okay? And this happens because dove is the best response to hawk. Here, remember, what is best response? Best response is determined as to, maybe we can go a step forward. So let's assume we are animal 1, okay? And let's assume that animal 2 is playing strategy hawk, Okay, so if animal 1 plays D against this strategy hawk, the payoff for animal 1 would be 1. But when playing strategy hawk against hawk, the payoff would be 0. So for organism or for animal 1, the best response to hawk, right, between these two, the best response, the response that gives the largest or highest payoff would be dove, right? So D is the best response to hawk. And in fact, hawk is the best response to dove. So we would also say that the pair of strategies HD, both the pair of strategies HD and the pair of strategies DH, they both are considered Nash equilibria. Okay, now the fact that a game has two Nash equilibria, that doesn't imply that we're able to identify an evolutionary stable strategy. So we consider this game, the hawk-dove game, in a setting where each animal is hardwired in terms of their genetic information to play a particular strategy. Okay, so and to anticipate or forecast what is going to happen in a hawk-dove game in the presence of evolutionary forces. So, I mean, when we're saying that we are now going to start considering this game in the sense of when genetics is playing a role. So this behavior is, we want to think of an animal manifesting a particular behavior as a function of some mechanism that is at the genetic level. Okay, so this phrase of being genetically hardwired to play a particular strategy. Please, when you read this, immediately think genetics and immediately have that image of genetics in terms of probabilities, right? Remember when we had that brief brief lecture on the basic principles of these genetic models, those principles in which you can write probability trees. We also talk about Punnett squares, right? But that's when we were first refreshing our memory as to what are genotypes, what are phenotypes. That's exactly the type of theory we want to now incorporate into these models. So to reason about what is going to be the outcome on the long term, we have to include, right? We have to rephrase this game in terms of evolutionary forces, right? So letting the the laws of evolution interplay with this genetic information. And in that sense, we need to have a general notion of what we consider stability, evolutionary stability. So let's review some, or let's write down some definitions. So far, we've been writing down the matrix of payoffs with two strategies, possibly three strategies, right? In general, you can have a discrete number of strategies. And we've been writing either in general form constant parameters for the values of the payoffs. So what we have been calling a strategy so far is typically what's referred as a pure strategy. We say that someone is employing a pure strategy when this individual plays that strategy in a game. On the other hand, we have now the definition of mixed strategy. And with mixed strategy comes randomness. And here randomness is translated into probability, okay? So for pure strategies, You can maybe rephrase this as either the extreme values of a probability, either probability equals 0 or probability equals 1. With those extreme values of probability, there is no uncertainty, right? However, when you consider mixed strategies, you are going to be associating certain events to non-extreme values of probability. So there is uncertainty, or events, in this case, strategies are going to be played out of basically a portfolio of possible strategies. And this ability to choose which strategies played out of a portfolio is an ability that's associated or is proportional to some probability. So for mixed strategies, we're no longer considering a discrete number of strategies, 2, 3, 4, 5 strategies. Okay, so it's no longer a discrete number. Instead, when we refer to discrete strategies, we are referring to the numbers between 0 and 1, because those are basically, that is exactly the portfolio or that set of possible strategies, is each of them corresponds to the numbers on the interval 0 to 1. So mixed strategies are going to be associated with behavior that we consider randomized behavior. In the sense, randomized means probabilistic. The behavior is subject to a probability, or the outcome, however, having that behavior, we observe that behavior, but here the framework, the theoretical framework, is that behavior is the outcome of a random experiment or a random event, an event that is subject to the rules of randomness or the rules of probability. Okay, so let's now, I'm giving you here basically just, instead of giving you a preview and then showing you the movie, I'm showing you first the end of the movie. So let me switch gears here for a minute, and we're going to take a look at this probability tree. We're going to take a look at this probability tree from the beginning. Okay, so we're going to use these probability trees to write down. This is in a very close analogy to how we first learned about these trees, right? And we did that when we were discussing phenotypes and genotypes. And now we want to use that methodology in the context of a mixed strategy game. So we have, just in the same spirit as we had with the payoff matrix, we're going to consider this game. And there are two organisms playing this game. So here is organism 1, organism 2, right? We're going to still, even though we're now considering mixed strategies, this schematic is inspired by the scenario with pure strategies, okay? So we still write what we're seeing here on the screen. Organism 1 corresponds to the first node there in green, and organism 2 corresponds to the 2 nodes there in blue, okay? So there is a, this is what I'm saying. We're gonna write information here. We're gonna write information corresponding to this organism 1, okay? So let me go back. Okay, so turns out that in the sense of pure strategies, when the probabilities have extreme values of 0 and 1, there are 2 strategies, but and they are D and H, right? So now we're gonna say that with probability P, organism 1 plays the strategy D, and with the complement 1 minus P, with probability 1 minus P, organism 1 plays strategy H. Okay, It will be similar for organism 2. We're going to use another letter to denote the probability. We're going to say Q. With probability Q, organism 2 plays strategy D, and the complement 1 minus Q is the probability that organism 2 plays strategy H. Okay, so we have completed the information along the branches of this tree, and now what would happen if we have that the individual, we have the outcome that the individual is playing along this branch. If it plays, organism 1 is playing D with probability P, and organism 2 is playing D with probability Q, this is not exactly in the sense of pure strategies. You would think of the pair of strategies D, D, and that will be associated with the probability P times Q. Okay. However, if organism 1 plays D with probability P and organism 2 plays H with probability 1 minus Q, that in the sense of pure strategies would be associated with D, H, and that would happen with probability P times 1 minus Q. Okay, so here the idea is what we had seen before. We are writing probabilities along possible combinations when we go one path, along the branches of this tree. So you can see how these other potential outcomes have these probabilities. Okay, so basically there are, in the sense of pure strategies, there are 4 potential outcomes, and when we associate probabilities, which are numbers between 0 and 1, then we come up with these terms: P times Q, P times 1 minus Q, 1 minus P times Q, and 1 minus P times 1 minus Q. If you write this as a Punnett square, you probably end up with very similar terms. And now we bring to light another piece of information. Remember those values of payoffs that we can also write in terms of this matrix in this form. Then the entry here on the 1-1 entry is, which just disappeared here, number 3 is going to be associated with the it's going to be associated with one of these possible outcomes, right? Every value in the matrix will be associated with one of these possible outcomes, with one of these possible paths of plays, right? So here is number 3 associated with the probability P times Q. Here's the payoff value of 1. Here's the payoff value of 5. And 0 is the payoff value associated with probability 1 minus P times 1 minus Q. We have gone over how this tree is, how every term in this tree is calculated, okay? And we are specifically interested on basically putting together this information. These values of probabilities, okay, are going to multiply the expected payoffs, okay? So now you probably you're likely familiar with the term expected value. So now we're going to refer to the payoffs in terms of the expected value of payoff or the expected payoff. Okay, so we refer to expected payoffs for mixed strategies. The space of strategies is not longer a discrete space or discrete, well, something you would probably connect to what they call discrete state space. Now a space of strategy of the strategies is map, if you will, to an interval, to the closed interval 0, 1. So we identify quantities, 2 quantities here denoted by P and Q, which are in this interval, and the expected payoff for strategy P versus strategy Q. So here is where I like to first point out that now instead of only writing H and D, which are 2 of the strategies, we are writing P and Q, where P and Q are values, are quantities that are in that interval, right? So now the strategies are denoted by these are probabilities, but they are also considered strategies, okay? P and Q are also considered strategies. So we say, or we write, the expected payoff for strategy P versus strategy Q. We use the notation E of P comma Q. This is E for expected payoff, right? E for expected payoff. So the expected payoff for strategy P versus Q is 3PQ plus 1 times P times 1 minus Q plus 5 times this quantity plus 0 times this. And where do these values come from? Well, they come from the calculation we did in the, they come from here. All those values are coming from collecting these terms, right? P times expected, the payoff times the probability of having that outcome, the payoff times the probability, the payoff times the probability, and so on, right? So we collect these terms, add them up, and that's what we define as the expression for the expected payoff of strategy P versus Q. 0 multiplied by that means that term vanishes, and now maybe we can, we cannot really simplify this any farther, but so this expected payoff formula takes a reduced form that looks like this. And let's now talk about what happens when one player is using strategy P, okay, or strategy Q. Let's say that one player is using strategy Q, and the expected payoff from playing D, let's suppose that the other player, okay, so here we have, suppose that organism, this was what we're calling animal 1 or organism 1, and this here is what we were calling organism 2, okay? So suppose that with probability 1, organism 1 is playing strategy D, okay? When organism 1 plays strategy D, if organism 2 plays strategy Q, then we may have these possible outcomes, right? So we may have that with probability Q, we would go along this branch and that branch, and that is multiplied by the payoff according to the payoff matrix. So here we have expected payoff of 3Q, but if instead we went through this other branch here, then we would have expected payoff of 1 times 1 minus Q, right? So that means the expected payoff from playing D would be the sum here of, it would be the sum of these two quantities, right? Which you will see here in a minute, 3Q plus 1 times 1 minus Q. And this is 3Q plus 1 minus Q, which is 2Q plus 1, okay? So now, on the other hand, the expected payoff from playing H, expected payoff from playing H. In that sense, we would assume that organism 1 is playing D with probability 0, which means that it's playing H with probability 1, okay? And organism 2 would collect the expected payoff of 5Q plus 0, okay? So, in other words, by visiting one scenario, we obtain expected payoff of 2Q plus 1, and by reviewing the other scenario, we would obtain a payoff of 5Q. We set these two quantities to be the same, then that would give us that Q equals, they're equal, these expected payoffs would be equal if or if and only if Q equals 1/3. Okay, so this quantity, this probability, but this is also a strategy. This strategy 1/3, we're gonna discuss about this. The 1/3 value for Q or P, we're gonna know this as P bar. This is a strategy. This is a mixed strategy, and is a mixed Nash equilibrium. Remember the notion of Nash equilibrium, the best response? So when we evaluate the expected payoff at 1/3, 1/3, right? Remember, we had in previous two slides, we had an expression for the expected payoff of strategy P versus strategy Q. So now what we're doing is evaluating the expected payoff at these values of 1/3, 1/3. You go back, plug in 1/3 for P, 1/3 for Q, and do some calculations, and you will arrive at this result. That the expected payoff for 1/3 versus 1/3 is 5/3. Now, that is the case. You will observe that 5/3 is also the expression you obtain when calculating the expected payoff of P versus 1/3. So you go back to this formula of E of P comma Q, plug in P and 1/3, and that will be equal to 5/3. This is left to you as an exercise. This expression looks like this, and you can easily also make the observations that you can realize that here the expected payoff for 1/3 versus 1/3 is equal to the expected payoff of P versus 1/3 for all values of P in the interval 0, 1. All values of P, okay? Also, remember, what we just discussed here was about the expected value of P versus 1/3. Now, so in the previous slide, we had expected value of P versus 1/3. Now we're referring to the expected value of 1/3 versus P. This is not exactly the same, very, very closely related, but not exactly the same. You plug in 1/3 comma P in that order and the general expression for the expected payoff, and you will come up with 4P plus 1/3. Okay, so we also like to note that the expected value of P versus P, the expected value of P versus P is actually a quadratic, a concave down quadratic. So this would be minus 3P squared plus 6P. This quadratic has roots at 0, and it has another root at 2. Okay, so in fact this quadratic looks like this. So what I'm trying to drive, the message I want to underscore here is that we're really only interested in values of P between 0 and 1, right? So we are going to make, and so why is this important? Well, this is important because of what goes on this interval. If you had a way of zooming in into this image there, right, something special is happening here. You can guess what that value of P is. Something special is happening there. So what we're seeing here is that for the values of P we're interested in, which are in the interval 0, 1, the expected payoff of 1/3 comma P is always larger than the expected payoff of P versus P. That happens for all values of P different than 1/3. Okay, and this is exactly the type of inequality we need to come up with a definition of evolutionary stability. So in this case, this result implies that the 1/3 is an evolutionary stable strategy, an evolutionary stable mixed strategy. And this concludes our discussion on mixed strategies.